Ocean currents and gyres. In the previous investigations, you've learned what happens when the sun's radiant energy heats Earth's surface. The ocean covers a whopping 70% of the Earth's surface. As the ocean heats or cools, how will all the water move? How will those movements affect weather and climate? The driving forces of ocean currents. Just as there are global wind patterns, there are global water patterns called ocean currents. There are three main forces that affect ocean currents: winds, differences in water density, and tides. Winds drive currents near the ocean's surface. In coastal areas, local winds can drive currents, but in the open ocean, global winds drive currents. Differences in water density. Deep ocean currents are driven mostly by differences in density of water. You learned earlier that convection currents form when fluids have different densities. What are two factors that could cause ocean water to have different densities? Which heats up more quickly, water or land? As you learned earlier, water heats and cools slowly, but even those slow changes will cause temperature differences in the ocean from one area to another. As the sun's radiant energy warms the ocean, differences in temperature will cause differences in density, resulting in convection currents. Which is more dense, a solution with a lot of salt or little salt? As you learned earlier, solutions with more salt are more dense. Variations in the concentration of salt, called salinity, in ocean water causes differences in density, resulting in currents. The combined effect of density differences due to temperature and salinity result in upward and downward flow of water masses. These currents occur at both deep and shallow ocean levels and move much slower than surface currents. The effect of temperature and density on currents is greatest in Earth's polar regions. As polar sea ice forms, the surrounding seawater gets saltier. This is because pure water freezes and separates from the salt, leaving all of that dissolved salt in the ocean. Water near the polar regions sink from being more dense, not only from cold, but also being saltier. As this cold, salty water sinks, the surrounding surface water moves in to replace it. Once the water sinks, it travels through the ocean basins, eventually coming back to the surface about 1,500 years later. This motion drives the deep ocean currents that weave their way around the planet in a system we call the Great Ocean Conveyor Belt, a huge convection current. Tides. The third main force that affects ocean currents is tides. Tides are driven by the gravitational force of the moon and the sun acting on the rotating Earth. Near shore, the rise and fall of water indicates with the shapes of shorelines to create tidal currents. Tidal currents follow regular patterns: flooding when the tide moves towards the land and ebbing when it moves towards the sea. The shape of the shoreline can dramatically affect tidal current. The Bay of Fundy between Nova Scotia and New Brunswick is a classic example, with tides of over 15 meters, the highest in the world. As you might imagine, aquatic ecosystems in coastal areas are dramatically affected by daily tidal currents. Rocks on the shore in Nova Scotia at high tide and low tide. Same place. The movement of ocean water is a complicated thing. Factors in the tides, density changes due to differences in temperature and salinity, local winds and global winds, and the Coriolis effect caused by the rotation of Earth, and you have most of the pieces to the ocean current puzzle. What's the final puzzle piece? The ocean is broken up by giant land masses of continents and islands. Just as water in a stream will flow differently if you drop a large rock, the movement of the ocean water is affected by the geology of Earth. Local currents. The pattern of ocean currents affect how fish and other sea life move around the ocean, control how ships travel through water, and sometimes carry swimmers far from the beach if they aren't careful. When a surface current runs close to shore, a visitor to the beach could experience a rip current. Those local currents form around low spots, breaks in sandbars, or structures such as piers. Rip currents can move faster than even Olympic swimmers can swim, and if you are caught in one, don't fight it. They are generally not more than 25 meters wide, and they usually break up not far from shore, so it's best to swim around them. Global current patterns. Ocean currents can form swirling areas called gyres. A gyre is a large system of rotating ocean currents driven largely by winds. There are 5 main gyres around the Earth's ocean, as well as other less major gyres, such as one that circles the South Pole. What causes these gigantic whirlpools in the ocean? Do you notice any patterns in the map of gyres? All of the major gyres occur in the middle of the spaces between continents. As ocean currents hit shallower areas of coast, they start to move in different directions. Think about water as sweeping along the coastline in a large-scale current called a boundary current. As the water approaches a continent and then sweeps in a different direction, you get the first part of a swirl that will ultimately form a gyre. A boundary current of the South Pacific Ocean is the Humboldt Current that moves northwards along the coast of Chile. As it veers away from Peru, deeper water upwells to replace the westward moving water. This is one of the biggest upwelling systems on Earth. It brings up cold, nutrient-rich ocean water, feeding an abundance of marine life, and the largest fishery on Earth. About 20% of Earth's fish catch is made possible by the Humboldt Current. Because the current is cold, it cools the water and the climate of Chile and Peru. Perhaps the most familiar of the boundary currents is the Gulf Stream in the North Atlantic. It goes northward along the east coast of the United States and then across the North Atlantic Ocean towards Europe. The warm water of the Gulf Stream affects not only the climate of the east coast of North America from Florida to Newfoundland, but also the west coast of Europe, making for much milder climates than would exist otherwise. The Great Pacific Garbage Patch. We see it every day. Someone carelessly drops a plastic cup or a wrapper or a mask on the ground as they walk, or tosses it out the car window. Where are those plastic objects now? Plastic doesn't biodegrade to break down in nature quickly, and trash on the ground can get washed by rainwater into storm drains that eventually lead to the ocean. Imagine all that plastic trash floating into the ocean and getting transported far from its source. Where will it end up? About 1,600 kilometers northeast of Hawaii, in the Pacific Ocean, is the Great Pacific Garbage Patch, a huge swirling current of garbage, mostly plastic and fishing equipment. The pieces can be as large as huge fishing nets, but are mostly pieces of plastic, the size of cornflakes or rice grains, broken from larger plastic objects. This gigantic ocean whirlpool of garbage doubles in size every decade. At the end of 2009, it was estimated to be roughly twice the size of Texas. The garbage is caught in what oceanographers call the North Pacific Ocean Gyre, one of the giant gyres generated by the world's ocean currents. The garbage includes toxic chemicals. Plastic doesn't biodegrade quickly, but it will break down into tinier and tinier pieces, just the right size for marine life to eat. Fish that feed on plankton eat tiny plastic particles, and toxic chemicals from the plastic leach into the fish tissue. Birds, such as an albatross, forage in the North Pacific and eat large amounts of plastic, including fishing line, light sticks, and lighters. Some birds purge themselves of plastic by throwing it up, but thousands die each year from eating plastic debris. Sea turtles, many species of which are endangered, may think floating plastic bags are jellyfish and accidentally consume them, which can lead to death.